Hello everyone, thank you for watching this video. My name is Alexander Black and today I will be talking about Deep Image Comparator, an approach to visualize editorial change. Imagine the following scenario. A creator authors some content that is then uploaded to a database, along with some metadata. But when the image is distributed around the internet, for example through social media, metadata can be lost. The image may undergo resolution, encoding quality, aspect ratio, and other benign changes, as well as editorial changes authored by other users that may affect the meaning or the story that the original image is aiming to tell. A user who encounters such an image could then use our proposed image comparator network, or ICN, to retrieve the original version of an image from the database. ICN then compares the query with the original and highlights areas of any editorial change if present, while ignoring any benign transformations. We propose novel contributions to both the retrieval and comparison stages of the process. For comparison, the best case scenario is fairly trivial. Assuming the original image is available, the edited part can be obtained by simple subtraction of one image from another. However, the query may be subjected to multiple in-place and out-of-place transformations, to which we refer to as benign transformations. For in-place transformations, we use the same augmentations as in ImageNet-C and random translation, rotation, and scaling for out-of-place transformations. To account for out-of-place transformations, we use a de-warping unit that relies on an optical flow between the query and the original to align them. We use draft for flow estimation, but it could be swapped for any other optical flow network. Then both the original and de-warped query images go separately through several layers of a backbone network, such as ResNet50 in this case. Produced features are then stacked together and used as an input for the later layers of the same backbone network. Then fully connected layers are used to produce two outputs: a three-way prediction, classifying the pair of images as either benign, manipulated, or two completely different images. And the second output is a 7x7 heat map that localizes the manipulated region. Heat map is zeroed out if the pair is classified as benign and is set to maximum if the pair is classified as different images. The network is trained end-to-end with cosine similarity loss for heat map and cross-entropy loss for classification. To train the network, we use a PS Battles dataset that consists of images from Photoshop Battles subreddit. It contains around 7,000 original photos paired with one or multiple manipulated versions. We conduct a user study using Amazon Mechanical Turk to obtain bounding box annotations for edited regions with 3 respondents per image. Bounding box annotations are then converted to a 7x7 heat map where the brightness of each cell is proportional to its intersection with their bounding box. This heat map is used as is during training and can be upscaled and overlaid on top of the image to outline the manipulated region for users. We use intersection of a union between the prediction and ground truth heat maps as our performance metric. We compare our approach to both classical and deep learning methods of forgery detection. Since these methods were not made with out-of-place transformations in mind, we evaluate their performance both with and without our geometric alignment unit. We show that ICN achieves a much higher IOU score than any of the other methods. Additionally, we conduct a blind user study using Amazon Mechanical Turk, asking users which of the outlines better matches the manipulated region. In this experiment, users prefer highlights produced by our method in 77% of the cases. This number is further improved to 85% if the smooth heat map is thresholded at a certain brightness level to produce a clearer outline. Here are some representative examples of model's performance. The leftmost image is the original, query is in the center, and on the right, the prediction in blue and ground truth in orange are placed on top of the de-warped query. But as you remember, we need to retrieve the originals first. We perform retrieval in 2 stages: near duplicate search, followed by re-ranking. For stage 1, we use ResNet50 pre-trained on deep augmix to obtain a 256-dimensional embedding that is robust to benign transformations. It is trained with a loss function similar to SimCLR, with 2 differences being that there are multiple positive images per input and manipulated images are considered to be positives. We then perform a 2-step quantization to reduce the size of the image descriptor to 128-bit. This allows for very fast search even in multi-million image datasets. In the next step, re-ranking, first top 100 retrieval results from stage 1 are rearranged using ICN's classification score. The first image ends up being the one with the lowest confidence of being different from the query image. For example, with the query image like this, stage 1 results will be as follows, which is further improved after re-ranking. To evaluate retrieval performance, we construct a database of 807 original images from PS Battles test set, plus 2 million diverse distractor images scraped from the Adobe stock website. We compare recall performance to both deep and classical image hashing approaches. We demonstrate that the first stage of our method achieves recall at 1 of 71%, higher than all other methods. We also show that stage 2 re-ranking improves the recall further to 87%. Additionally, we demonstrate that the comparator can be used to highlight edits in video by comparing one frame at a time. Robust video retrieval, however, is outside of scope of this work. Thank you so much for watching. If you have any questions, feel free to contact me or any other authors via email.